Have you ever really stopped to think about what happens when you turn on a light? I mean, we do it every single day, but behind that simple flick of a switch, there's this invisible, incredibly powerful world at work. Well, today, we're going to pull back that curtain. Let's dive in and explore the fundamental forces that power our lives: electric current and resistance.
So, let's start right there. What is actually going on inside those wires? It's not magic, I promise you. It's physics. We're about to take a little journey, starting with a simple light bulb and ending up at the massive grid that powers our entire cities. And the best part? It's all based on just a few simple, elegant rules.
So, to get started, we first have to wrap our heads around the idea of flow. In the world of electricity, this isn't just any flow, it has a very specific name. And that name is electric current. Honestly, the best way to picture it is to think about water flowing through a pipe. Electric current is exactly like that. It's just the amount of electric charge that's zipping past a certain point in a certain amount of time. The more charge that flows by every second, the higher the current. Simple, right? But here's the catch, and it's a big one. Just like that water needs a complete, unbroken pipe to flow, electricity needs a complete, closed path. We call that a circuit. You can see it here. The path has to go from the battery, through the light bulb, and all the way back again. If you cut that path anywhere, if you break the circuit, the flow stops instantly and the light goes out. Now, we need a way to measure this flow, and we do that with a unit called the amp, or amp for short. It's named after the French physicist André-Marie Ampère. So when we say 1 amp, what we really mean is a specific amount of charge, 1 coulomb's worth, is passing by a point every single second. It gives us a really precise way to talk about just how much electricity is moving. Okay, so if current is the flow, what happens when something gets in the way? Because in every electrical circuit, there's always something pushing back, some opposition to that flow. Let's stick with our water analogy and see what that looks like. That opposition has a name too: electrical resistance. Let's go back to our water pipe. Resistance is like making that pipe narrower, or maybe even filling it with a bunch of gravel. It just makes it harder for the water to push through. In a circuit, resistance makes it harder for the current to flow, and we measure it in a unit called ohms. So what determines how much resistance something has? Is it just random? Not at all. It's actually governed by this really important formula. Now, it might look a little intimidating at first, but I promise it's pretty straightforward when you break it down. Let's look at each little piece. There are really just 3 main things to think about. First up is resistivity. That's just a fancy word for how much a material itself naturally fights against electricity. Then you've got length. This one's easy. Just like a super long pipe has more friction, a longer wire has more resistance. And finally, there's area. Think about it. A wider pipe lets more water gush through, right? Well, a wider wire, one with a bigger cross-sectional area, has less resistance. And wow, this table really drives home how much that first factor, resistivity, matters. Just look at these numbers. Copper, which we use for pretty much all our wires, has an incredibly tiny resistivity. It basically lets electricity flow right through. But then look at fused quartz, an insulator. Its resistivity is, well, it's astronomically higher. It's a number so big, it's hard to even imagine. And that is exactly why we wrap our copper wires in plastic or rubber, to keep that electricity contained and going only where we want it to. And resistance isn't always a bad thing. In fact, it's so useful and so important for controlling electricity that we've actually made components specifically to provide it. These little guys are called resistors. They are absolutely essential in electronics for controlling how much current flows to different parts of a circuit, making sure all the delicate components get exactly what they need. Okay, so we've got current, which is the flow. We've got resistance, which is the obstacle. But what about voltage, the push that gets the whole thing started? How do all 3 of these things relate to each other? Well, it turns out there's one beautifully simple law that ties them all together. And here it is, Ohm's law, named after the German physicist Georg Ohm. This is basically the golden rule for simple circuits. It says that the voltage, the push, is equal to the current, the flow, multiplied by the resistance, the obstacle. What's so amazing about this is that if you know any 2 of those values, you can always figure out the third. It's incredibly powerful. So using Ohm's law, we can figure out how circuits behave. And when it comes down to it, there are 2 basic ways you can connect things. On the one hand, you have a series circuit, where everything is lined up in a single file path. And on the other, you have a parallel circuit, which gives the current multiple paths to take. This one little difference completely changes how the entire circuit works. All right, so that's the theory. But why does any of this really matter?
How do we actually use these ideas in the real world? Well, let's talk about power and what these different connections really mean for us.
Understanding this difference is absolutely crucial. In a series circuit, there's only one road for the current to take. But in a parallel circuit, the current can split up and take different paths. Now think about your house. It's wired in parallel. And thank goodness for that. That's why you can turn on a lamp in one room without turning on everything in the whole house. And it's why every single one of your outlets provides the same amount of voltage.
And this all leads us straight to the concept of power. You see this word all the time. When a light bulb says 60 watts or a microwave says 1,000 watts, that's a measure of electric power. It's simply the rate at which that device is using electrical energy. And to calculate it, all you have to do is multiply the current flowing through it by the voltage pushing it. Now, here is where it all comes together in a really clever way. Power companies have to send electricity over hundreds of miles, right? But the long wires themselves have resistance, and that resistance causes some of the power to get wasted as heat. The formula for that wasted power is current times squared times resistance. So, to minimize that loss, they do something brilliant. They send the electricity at incredibly high voltages. Because power equals current times voltage, if you crank up the voltage, you can deliver the same amount of power with a very, very low current. And a low current means you lose way, way less power to heat in the wires. It's an absolutely genius solution that saves a ton of energy.
So, there you have it. We've gone from the invisible flow of charge inside a single tiny wire all the way to the incredible engineering that makes our global power grid possible. And everything from the processor in your phone to these giant transmission towers, it's all governed by the same fundamental principles of current and resistance.
It's really kind of mind-blowing to think that these simple, elegant rules are the foundation for our entire modern technological world. It really makes you wonder, as we get better and better at using these forces, what's next? What new technologies, what new futures are we going to power up next?